Hello, everyone. This is Hanney Seylim of Critical Faculty. Today, we are going to race into a very important subject, please allow me to welcome Professor Krauss once again to Critical Faculty. Good day, Dr. Krauss.
Hi, and let me apologize for the fact that today I have to rush off because of an unexpected engagement. So we'll be quick, and I'm not doing you justice, but I'm happy to be back.
Thanks very much. I think we'll split this into two parts then. And we've had a discussion before going online about the seemingly disjointed title of the video, but it's basically the multiverse, quantum mechanics, and we'll probably start with quantum mechanics, multiverse, and then God, and how they all link together. Um,
Three big topics.
yes,
Well,
indeed.
two
Yeah.
big topics anyway. Okay.
Well, the quantum mechanics has always been, or of recent times, has been used as a catalyst for something spooky out there. It started with Einstein not accepting indeterminacy in the Copenhagen interpretation because he believed that God doesn't play dice with the universe.
Which was just a quip, by the way, for those who think Einstein believed in some personal God. He didn't.
Yes.
Anyway.
But the question is the duality, the fact that only things manifest when you start looking at them. Apparently,
Well,
is
I
that
mean,
myth?
yeah. Well, quantum mechanics is very, very weird. There's no doubt about it. It's not as weird as some New Age people suggest, but it's very weird. And quantum mechanics is based on some properties that just seem impossible classically, but that's just the way the world works. To me, it's not so much that things, don't aren't in a don't exist or something till you don't see them. That's not true. But what happens is that quantum mechanical objects can exist in many different classical states at the same time, and when you measure them to be in one state, and that's a property of the measurement process. But you can't say that they were in that state before you measure them. In fact, you can prove that they weren't in a single state before you measure them. And so, like it or not, that fact that quantum systems can be in what's called a superposition of different states and are only put in a single state when you measure them, is just a property of quantum mechanics. And it may sound crazy, but it is the way the world works.
Very, very interesting because it's been used as the observer effect, and the fact some people would use it as things will only manifest. I think Einstein said, "Don't tell me that the moon doesn't exist when I look at it, when I don't not look at
If you
it."
look at well, that's the problem. Point is that what it says is you can't. And Einstein would have appreciated, I'm sure he did when he debated with Bohr, the statement that you have to be operational when you talk about physics, because he was famous about thinking of operationally what certain things mean. People took time for granted, or simultaneity for granted, and he asked, "Well, how do we measure it? Or what's operationally?" And he proved that what we took for granted was not true. Well, we take for granted that something we haven't yet observed is in some state before we observe it, and the answer is, well, that taking that for granted is just wrong, and and calling it the observer effect unfortunately gives people the notion that it has something to do with people or psychology or mental perception, and it's not. I mean, when a particle collides with another particle, it effectively makes a measurement. It has nothing to do with people or consciousness or anything else in that regard.
Um, so the question here: do you think electrons are standing waves around the nucleus of an atom?
Well, I mean, in a sense, the orbitals are, you can think of them classically as standing waves. In fact, that's how Louis de Broglie first calculated the levels of an atom by saying that it is well known in quantum mechanics that the wavelength of a particle is related to the wavelength and the wave function of a particle is related to its momentum. And therefore, if you want to have anyone knows that on a string of a certain length, you can only have certain standing waves at certain frequencies. And he argued that more or less, if you have an orbital, then you can only have waves that are standing waves if there's certain frequencies. And that heuristic picture worked. We think of it more. We don't think of them as classical standing waves anymore. We just think of them as stable quantum states. But you get the correct number by thinking effectively of standing waves, at least to first approximation.
One of the catalysts used in quantum mechanics and used by the religious people is the causality, because obviously they're using the causality and the contingency to prove an essential primary being or creator. Causality. I mean, there are many different interpretations within quantum mechanics. There is the Bohmian, there is the Everett. Which one appeals to you most, or which
Well,
one?
look, they're all, when you talk to me about a lot of these interpretations, and once again, you're talking about classical interpretations of quantum mechanics, which are pleasant to think about, but they mean nothing. In the sense, the world isn't classical, and any classical picture of quantum mechanics is just a kludge. A lot of people make a big deal about these classical pictures, but they are just ways, they're just crutches for people to think. We all think classically because we see the world classically, but they don't capture. But the quantum mechanics, we should, as a late friend of mine at Harvard, Sidney Coleman, used to say, we should think of the interpretation of quantum mechanics, but not or rather the interpretation of classical mechanics, not quantum mechanics, because classical mechanics is an approximation of quantum mechanics, and so we shouldn't expect any classical picture to kind of make a great deal of sense in that regard. But the notion of causality, even, I mean, quantum mechanics is deterministic, which means it's based on second order differential equations. If you define the wave function at one time and you know all the forces, you can determine the wave function at some further time with 100% accuracy. Now, you won't determine the measurement of how you measure that wave function, but the underlying physics is completely determined. But causality is interesting. When I have a light on right next to me now, I know that when I send electricity through that light bulb, there's a probability that photons will be emitted by the excited electrons in that system. But each atom, when it emits a particle of light, there's no direct cause in the sense that I can't say it just happens. It's spontaneous. I mean, I can say with a probability that it happens, but I cannot say at that instant there was a precise cause for that atom to emit that photon. I can say that atom will emit a photon with some probability over time, but why that time rather than some other time? Can't say. So in some sense, this notion of things happening spontaneously without an immediate proximate cause is already obviated in quantum mechanics.
So do you think, Dr. Krauss, that there are yet to come an interpretation that originates from the bosom of quantum mechanics, the quantum understanding, rather than classical, then translated into quantum mechanics, something from within?
Oh, I don't really understand that question. Sorry, go on again.
Like a different interpretation of quantum mechanics that doesn't start with classical physics and then transition.
The point is, we don't need interpretations of quantum mechanics. We have quantum mechanics. Yeah. It's like saying we have to have a translation of Dostoevsky or and we don't need to. We have Dostoevsky in the Russian. Now, I can't understand it in the Russian. That's my problem. So I have a translator, and it probably loses something in the translation. But so just as quantum mechanics loses something in the translation. So I guess we have the equations of quantum mechanics. We have well-defined rules. They allow us to calculate and make predictions, and those predictions agree with observations. I don't, and everything else is kind of philosophy, if you wish, for me.
So the last question on the quantum mechanics, I think we move to the next topic pretty quickly. Entanglement has been used as another spooky situation here, and I think it's misunderstood because there are people who are thinking that actually information travel faster than the speed of light, and there's actually information that travels at all.
No, that's not the case. But I think I have to. Schrodinger tells me I'm supposed to hold on a second. Wait a second.
That's all right.
So my cat was in a box, and I think I had to determine if he was alive or dead.
At least we know it's alive.
But anyway, I'm sorry, I'm out of focus now. I'll get this camera to focus on me, hopefully. Come on. Okay. There we are. And anyway, entanglement. There's no information. Entanglement is spooky action at a distance. I agree with Einstein, but it's spooky action distance because, once again, classically, we think of two particles that are separated as two separate particles. But if they were initially in a single quantum mechanical wave function, they're really not separate particles. They're both part of the same quantum mechanical wave function. And it's not surprising, taking my cat as an example, that if I pull its tail, it meows from its mouth. It's not the tail and the mouth are connected. Now, the quantum mechanical entanglements are much more exotic and weird than the connection between my cat's tail and its mouth, but they're somewhat the same. The point is, there's no information that you can't send a message faster than light. Just because measurement of a particle here will instantaneously affect measurement of a particle here, doesn't. You might think it allows you to communicate, but as one can show, if one has enough time, and it's pretty easy, that there's no experiment you can do that allow you here to do something that would allow an observer over there to know that you've done something, and therefore to get the message from you. Simply because, I mean, I can explain it in 15 seconds, I suppose. An electron can be up or down, spin up or down. So if the two electrons are correlated initially, and one has spin up and one has spin down, but they can be in any direction. So they're opposite. They have opposite spins, but they can be in any direction, okay? Quantum mechanically. But then they move, and I measure one electron, and suddenly, boom, I measure it to be pointing in this direction. That tells me the other one is spinning in that direction. So you might say, wow, I can know there's a measurement. But the point is, 50% of the time, if I measure this electron, it'll be spinning up, and 50% of the time it'll be measured spinning down. Similarly, this other electron, if I measure it, 50% of the time it'll be spinning up, and 50% of the time it'll be spinning down. You don't know that when you measure it to be spinning down, that's because this other one has been spinning up. There's nothing you can do, and it's kind of a catch-22 that tells you that although there's a spooky action at distance, it doesn't allow faster than light communication, and therefore doesn't violate causality, among other things.
Well, I think Einstein sort of talked about the pair of gloves. If they were linked at the initial stages, of course, if you open a box and find the right hand side of the glove, then the other box will always contain the left hand side. It's just no mystery because they have been linked at the very beginning.
Yeah, and it's more sophisticated than that in quantum mechanics, because once again, the block is not, in the box is in many different states in quantum mechanics, and that's where people get hung up, because somehow, because it's in many different states, the other one is in many different states, and yet when you measure one, effectively you're fixing the other, and it's just a property of quantum mechanics, and it's weird, but it's been measured, and it's true. It's a property of quantum mechanics.
So we're going to stop talking about quantum mechanics, and we're going to move to the multiverse, and I think we'll end that, and maybe the second part in the next few weeks we can then talk about God, because then it will be quite linked.
As I told you, there are two important topics here. That's quantum mechanics and the multiverse. The last one is multiverse.
I know, we're doing them in 10 minutes each. But this is the world we live in at the moment. Everybody likes everything in 2 minutes.
Yeah. No, it's just saying the third one we can do without. It's not so important. That's what I'm saying. The first two are interesting topics.
Occam Razor will remove that for sure.
Okay.
Now, the Kalam cosmological argument. William Lane Craig uses the infinity, and I think he uses a fallacy of composition. He uses our common sense to understand the world we live in normal natural numbers, and uses something else. It's almost like using the laws of within the universe, inferring it to the universe itself, which always fails on its face. He's claiming that infinity leads contradiction, but mathematicians and physicists like yourself would say that no, we deal with infinity all the time.
We certainly deal with infinity all the time. We use it in mathematics, and it's vitally important in mathematics, and it's well defined, and various kinds of infinities are well defined. Physically, we have a harder time with infinities as a rule, for infinite density, infinitely large universes. But in fact, there's nothing that says that either of those is physically impossible. And indeed, the universe could easily be infinitely part of a space that's infinitely large. And I suspect that our local space isn't, but there's no philosophical rule that says it can't be. And I've debated Lillian Craig, and he uses classical logic and misquotes physicists to try and argue that science somehow proves there's a God. And come on, anyone knows that's not the case. Science doesn't disprove the existence of God, but to claim if science proved the existence of God, then in some ways, then everyone would accept that. And the fact that many scientists don't buy it, suggests that somehow what he's saying isn't correct.
Yeah. Well, he uses Alexander Vilenkin and Alan Guth, and they came in the video and said, we've told them right, left, and center. That's not never what we meant. I think Alan
I
Guth
tried,
said, we
yeah,
never
I
said
tried
the
to do that
universe
debate
had a
with him, and he
beginning.
claimed I was distorting what Alex Lincoln said, and of course, I wasn't.
Yeah.
Well, I'm happy. It would be fun if he said Alex Lincoln was distorting what he said, and I guess he can't do that.
Well, the story was he said, well, I never said that the universe had a beginning. He said inflation had a beginning. As a matter of
Yeah.
fact, there's a growing understanding that the singularity wasn't the ultimate beginning.
And let me make it even clearer. If the universe had a beginning, that still doesn't prove the existence of God.
Yeah.
You know, that photon that was just emitted by my light bulb had a beginning too, but it doesn't. But it doesn't prove that God made it, be emitted by that electron. And so, just claiming, even if our universe did have a beginning, and we don't know the answer, but even if it did have a beginning, it's not proof that there's a God. To claim that is to misunderstand, or to misunderstand physics, certainly, but to overstate and to use an idea beyond its domain of validity.
Well, infinity is such an interesting property because it's not a number. It's almost like a zero. It's not a number. But to play around with it, it's quite easily. He uses the Hilbert Hotel, which is, I think, it's fallacious.
Infinity allows lots of crazy things to be done. Mathematicians, however, have spent a lot of time figuring out how to make well-defined those crazy maneuvers, so that infinity can be treated in mathematical calculations. And I think it's fair to say that physicists, that mathematicians love infinities in a way.
Well, isn't it Ramanujan summation that is there? It is all natural numbers. There's a sum of, is it minus 1/12 or something?
Yeah, well, it's the zeta function. Riemann zeta function. That this, if you do it properly in mathematics, and I've talked about this in one of my books, it's the foundation of string theory. That
Yes.
in mathematics, if you add 1 plus 2 plus 3 plus 4 plus 5 and add that to infinity, you can well represent that sum by minus 1/12, which just seems insane. But it makes some mathematical sense. And as I say, it's the basis of why original string theories were 26 dimensional. And it's sort of, so, there are lots of things that seem to defy common sense in the world, and no one says the world has to obey common sense for you. And we what is common sense for us is common because we see the world on a classical level. We see the finite world, and therefore our experience doesn't encompass the world beyond that, and therefore it's not surprising that the world beyond the realm of our immediate experience it doesn't necessarily satisfy what we might call common sense. But that's okay. As I say, we are limited in our intuitive understanding of nature because by the limitations of our senses. And one of the great things of science is that it's allowed us to extend our senses and extend beyond our intuitive understanding to try and understand how nature actually works rather than how we want it to work.
I think in the past I heard you speaking about the strings theory, and you weren't quite convinced. Have you changed your position over the years? Has it?
No. No, I'm very impressed with the mathematics of string theory and some of the utilities of using that mathematics to understand certain physical situations. But I still see no evidence. I mean, I'm impressed with the theory, and I'm impressed with the ability of people who deal with it. But I still see no evidence that it describes the universe in which we live yet. But that doesn't mean I don't think it does. I just see no evidence that it does yet, and therefore I don't think it's neither not useful. And that's a bunch of double negatives. But I mean, the point is, I think it's worth exploring the theory, absolutely, and it can reveal lots of interesting things. But we shouldn't say it does what it doesn't do.
Does it meet Kuhn's falsification? Can it be falsified?
Well, we don't know yet. I mean, that's what because it doesn't make predictions yet about things that we can measure. we don't know. It's not currently falsifiable, but that doesn't mean it's not ever falsifiable.
Yeah.
Just like I said, just like I said, not understanding is not evidence for God; it's evidence for not understanding. And similarly, not being able to falsify something doesn't mean that we will never be able to falsify it. I mean, we couldn't have early days have falsified the existence of atoms, but now we can falsify it and find out, in fact, that atoms really exist.
We got 3 minutes to go before the 25 minutes we said we're
Yeah.
going to go on to for today at least. And I'd like to maybe put these two things together. Do you think quantum mechanics, the world at the very, very small, might carry some clues to the bigger picture?
Of course it does. That's why I do the kind of physics I do. The amazing thing about our universe is that it's expanding, and therefore it was once very small. And I've written books about this at a very early time. The entire visible universe that we now see existed in a size smaller than that of an atom. And therefore, to understand the initial properties of our universe, we have to understand the physics of the very small. By the same token, if we want to learn about the physics of the very small, we, in some ways, can look at the universe on its largest scales, because the remnants of what happened at those early times, some remnants, not all, some remnants may be preserved. So we can use the universe as a laboratory to measure particle physics. And that's why I, as a particle physicist, first got interested in cosmology, because I realized it allowed me to a new avenue to explore fundamental physics. And it has allowed that a great deal. And that symbiotic relationship between the very small and the very large continues. It was best exemplified by my friend Shelley Glashow, who first referred to it as Neuroboros, which you may know is a snake that eats its own tail.
Yeah,
And
or
in
of
some
course,
sense,
yeah.
you go to the very large, eventually you'll get to the very small again.
Yeah, this is really interesting. So with the you think that the very small might carry some clues to the larger world out
Of
there?
course it is. We see that, and we hope that I've written about gravitational waves from the beginning of time, which may reveal the earliest moments of inflation and things that we might not, or maybe even the existence of other universes, all sorts of things that we may have access to if we're lucky, by looking at the large scale universe and understanding that its properties come from the earliest moments, and therefore the fundamental physics on the smallest scales.
Final questions, Dr. Krauss. The James Webb Telescope extensions like these, tools like these, we've been devising for years now. Would it yield any interesting or new information because of its ability?
What tools? I'm sorry.
The James Webb Telescope.
Oh, of course it will. I've written about that too. You can read my tweets about that and my writing about that, and I even did a video on my podcast about the tools. But James Webb will hopefully tell us about the first stars that ever formed, the first galaxies. We'll learn about the nature of galaxy formation, of black hole formation, which may reveal the nature of dark matter. James Webb will also be able to, in principle, look at atmospheres of other planets, looking for signs of life elsewhere in the universe. And more importantly, every time we open a new window on the universe, we're surprised. So I still suspect that the most important thing that James Webb will discover is something we don't even know yet exists.
Professor Krauss, we are so grateful for your knowledge. I'm very happy that I keep having you on my channel, and hopefully we get in touch and have a second part to this when it's convenient for you.
Sure. Again, I'm sorry I have to rush off, but thanks again. I really do enjoy our discussions.
Thank you very much.
Okay.
Cheers, Dr. Krauss.
Thanks.
Thank you.
Bye.
All right, folks, thanks very much for tuning in. There will be a second part to this. This was supposed to be going for 45 minutes to an hour, but unfortunately, Dr. Krauss had a sudden arrangement. So please stay tuned. In the next few weeks, we'll have a second part to this episode. We talked about quantum mechanics. We talked about the multiverse, maybe not in detail as much as we wanted to, but we want to link them to God. Where does God sits amidst the two big theories of the world, the quantum mechanics, the theory of the very, very small, and the world at large, or the universe, or existence at large, because we're not going to be just talking about the universe that we live in, our local universe, but what everything that could exist, which is a multiverse, or the canvas of existence itself. So please stay tuned. We will be back in a few weeks with Dr. Krauss again, finishing up this conversation. I'd like to thank all of you and wish you a good day.